Dear students, welcome and thank you for tuning in. We are continuing our discussion about ceramics as part of the material science class and the biomaterials class. Here we're going to look at where can we find the elements that make ceramics in the periodic table and talk a little bit more about the properties of metals and non-metallic elements of the periodic table and how do they relate to ceramics and the bonding in ceramics. This is a picture of the periodic table. We are all familiar with it. We would like to distinguish two regions in this periodic table. This region in the yellowish color and this region here in the purple color. So this region here are the region that represent metals, and most of the elements on the periodic table are metals. I think there are 88 of them are metals. This purple region is the non-metallic elements. Ceramics are made of non-metallic inorganic elements, and they can be combined between the two, metallic and non-metallic. This is another schematic or representation of the elements in the periodic table. Everything in green is metallic and everything is on orange are non-metallic elements, and there are some in the middle metalloids. That's what we call them. Now let's go to look into what are the characteristics of the elements here, the green elements, what are the metals, and what are the characteristics of the non-metallic elements. So a quick review: most elements are metals, 88 elements in the periodic table. To the left of the strip stairstep line are metals or metal-like elements. So what are their physical properties? You can read them and you can see they're shiny, they reflect light, they're good conductors, they have high density, high melting point, they're ductile, so you can shape them easily into the shape or the form that you want to do. And this is one of the applications. This is one of the reasons why we like metals in engineering, because we can shape them the way we want. Malleable, also most metal can be hammered into thin sheets, so it comes down to ductility. So that's one of the reasons why metals are widely used in engineering. Also, this is physical properties of metals. The chemical properties of metals: they easily lose electrons when they are surrounded, let's say, under the certain conditions, and they corrode easily. And we will discuss corrosion later on. And corrosion, it is an electrochemical reaction. So we have chemical reaction, and there is an electrical electrical unit that is formed to result in a corrosion, and we're going to discuss that in details. So those are the characteristics of metals, and for us as engineers, it's important to understand them, because degradation, because of the chemical property in losing electrons and corrosion, is a determinant factor in engineering applications. You don't want to have corrosion or degradation of your components if you are building in to withstand loads for long periods of time. So, and also it's conducting energy and heat, and it's high density. So all of these things, but you need to balance what do you need for the application that you're looking for. Ductility is important in malleability, perfect. However, corrosion is a challenge in metals. That's why we look at non-metallic elements. So they're found to the right of the stairstep. So as we mentioned before, they're here. And those elements, characteristics are opposite to those of metals. So they're dull, they're poor conductors, they're brittle, very poor ductility and malleability, low density and low melting points. Now, here's what happened. Also, they tend to gain electrons and they don't corrode. So it's opposite to metals. That's why they can interact with metals and create different elements than or elements that are made of metals and non-metallic elements. Now, we talked about ceramics before, and we said that they are in their properties. We mentioned that they are they're made of inorganic non-metallic elements, and they are always composed of two or more elements. And we mentioned something about partially or totally ionic. It's very important. And if it's not totally ionic, if it's partially ionic, it means that it has also covalent bonding. We need to identify how much of our bonds are ionic or covalent percentage-wise. And this brings us to the concept of bonding in ceramics. And according to Linus Pauling, he's a chemist American chemist, biochemist, and chemical engineer. He did a lot of work and research. He published 1,200 papers and books, and I think 850, more than 850 of them are scientific topics. So he's a pioneer in chemistry and chemical engineering. So he came up with this concept called the ionic character. How much of my ceramic is ionic bonding and how much is covalent bonding? And he said that you can characterize the ionic nature of the bonds in a ceramic using something called the relative electronegativity. We talked about electronegativity before, so that some elements are more electronegative than other elements. So you can calculate something called the percent ionic character by 1 minus exponential minus 0.05 multiplied by xa minus xp. These are the A and B are the elements that create my ceramics, and the x's are the relative electronegativity, and you can get a number. For example, for typical ceramics, aluminum oxide, the maximum possible ionic character is only 60%. So 60% of the bonds are ionic, while 40% are covalent in this. Now, there's a lot of, it's important, and there's a lot of applications of how much do we need the ionic character to be. So it's a very important quantity to be identified. And if you're working in your project, I would recommend that you will, if you're working with ceramics, to find your ionic character for the material that you're using. So both ionic and covalent bonding is classified as strong bonds, and therefore most ceramics have high melting point, are stiff, hard, and corrosion resistance, and brittle. So are not always easy, and the brittleness comes from the fact that dislocations, which is the alignment of atoms in metals, they don't move easily under stress, and therefore ceramics are brittle, so they don't deform plastically, and because the movement of dislocation is the reason why metals deform plastically, right? So hopefully this introduces a little bit more about the bonding in ceramics, and it give you some more information. If you want to learn more about this ionic character, so this is a list of examples of ceramics materials, and it can show you the percent ionic character. So you can see carbon silicons are 12% are ionic, and the rest is covalent, up to calcium ferrite. I think that's also calcium ferrite. That's 89% ionic, and 20% is covalent. So each of these elements has a specific property that will result in using it in a specific application, and all of this number depends on the electronegativity based on the formula that Linus Pauling has suggested to calculate the ionic character. I hope that was helpful and you got more information about ceramics and its internal structure. Thank you for watching. Until next video. Bye.